Okay. So today is a momentous day. In fact, this is, in my opinion, and in many people's opinion, the most important results in calculus, and it has a similarly pretentious name. So in Act 2 and 3, we will prove two variants of the fundamental theorem of calculus, so usually abbreviated FTC. Sometimes people just use this term fundamental theorem to refer to either of these, whichever one they're speaking about at the moment, they'll just use that term. But for clarity, I want to distinguish between two formulations of it, which will both be useful. And in doing this, I'll also try to highlight one of the very common and very damaging misconceptions that people have about the FTC when they first learn it. But okay, that'll be the plan for today. First, we need to finish up a thing we started last time, where I was trying to convince you that if you do this process where you start with a function and then turn it into another function by integrating, finding the area under the curve of that guy from some base point, that this arrow, this machine that turns this function into its integral, always increases the niceness. So for instance, it will make this guy continuous if he wasn't already. So we'll prove that, and then we'll do the main event for the evening. Good. Thoughts or questions on the plan?
I have no questions.
Cool. Okay, let's finish up this proof from last time. So you'll recall the intuition that I was trying to build, that if you take a function that's already well behaved, like a line, and integrate it, now you get a line with a different slope. So it's certainly no worse behaved. If you take a function with some bad behavior, like a jump discontinuity, it gets turned into some reasonably good behavior, like a kink. A point discontinuity gets just completely flattened. It makes it go away. And similarly, here's another jump discontinuity, which is turned into a nicer kink. And a kink is turned into a kink in the derivative, which is even better in some sense. So it's becoming smoother, is what I'm trying to argue. So we'd like to make this a little more precise, but first we'll need an intermediate result. I'm tempted to call it a lemma, because we're moving towards this integration increases niceness result. But as it turns out, this thing is very important in its own right, so we're going to need this. So here's the lemma, which is actually a theorem, and it's very easy to prove. You can see it all.
Before anything,
Yeah.
why do you need to prove the statement that integrating increases niceness?
We don't have to.
Niceness on our scale?
Well, I'll make it more precise. The theorem that we're actually going to prove is that if a function is integrable, then its integral is continuous. That's what we'll prove. So increasing niceness. This is a sloppy, advertisement for the result, but this theorem is the precise statement.
Okay.
That's okay. I think I was supposed to name this. Yeah, I was supposed to name this. So this is supposed to be called Theorem 1 because I'm going to refer to it later. So this is Theorem 1. Okay, so it's actually quite straightforward. So we have any function f which is supposed to be integrable on some range from a to b. And suppose that you pick two numbers, lowercase m and capital M, which just strictly bound, well, not strictly, it could be equal, but it upper bounds and lower bounds the function. So everywhere on this interval, the function f returns some output which is always greater than or equal to the lower bound m and less than or equal to the upper bound capital M. So it's kind of intuitive. You might look at this and say, okay, well, certainly whatever this integral, if it exists, whatever this green integral is, well, it's certainly going to be bigger than the area under this lower bound, which I'm shading in yellow, and it's certainly going to be smaller than the area under this upper bound capital M, this extra stuff here, because it lies strictly, well, not strictly, but it lies between the two of them, so the area should as well. Yeah, so in other words, the statement we would like to prove is that the area under f between a and b is less than the area of this small rectangle down here, which, as you can see by geometry, is m times b minus a, and the integral should be less than or equal to this guy, area of the big one. Okay, so it's very straightforward to prove. You probably see immediately how to do it. You can just think about the very coarse partition. Think about the partition P, I don't even know what to call it, P2. It's a partition with just 2 points. Think about the partition which just has the points A and B. right? So that's the 2-point partition. The lower sum in this partition is certainly going to be, let's see, so since f is always greater than or equal to m, then its infimum on the whole thing must also be greater than or equal to m. So apparently the lower sum in this partition is greater than or equal to m times b minus a. But we know that whenever you refine a partition by adding points, right, the lower sums always get bigger. So I guess there's a skip step here. But the argument goes that m times b minus a is certainly smaller than the lower sum in the partition P2, because I guess the infimum of this function is greater than or equal to lowercase m, but this guy in turn is always less than or equal to the lower sum in any finer partition, right? Because refining always increases lower sums, or equal. Same thing but backwards in the upper sum. You could even skip the P2 step if you wanted to prove this directly. You could just say U, by definition, is a sum of infima on subintervals times b minus a, and every one of those, did I say infima? I meant suprema. U is the sum of suprema times b minus a. All of those suprema on subintervals by construction, this guy is always less than or equal to capital M. You could say this is simply less than or equal to m times the sum of all of these. Why did I write this as b minus a? Ti's, there we go. Ti's minus ti minus 1's. And then you could simply argue that all of the m sub I are less than or equal to m, and the sum of these differences by the telescoping argument is b minus a. So you could either prove this just by arguing the bound term by term in the sum, or by doing the 2-point partition and using the refinement argument. Either way, it's a very, very straightforward, two-step thing. So anyway, we've now proven that in every lower sum, every partition, you get a lower sum greater than or equal to lowercase m times b minus a. And in every partition, you get an upper sum, which is less than or equal to capital M times b minus a. And since the integral, by definition, is the supremum of all the low guys, which is equal to the infimum of all the upper guys, this thing must also satisfy these inequalities. So that means the integral lies between those two. Right, so that's the result we wanted to show. Pretty straightforward, but it turns out to be useful in several places. So this is Theorem 1 again. Good. Questions on Theorem 1?
I have no questions on Theorem 1. Theorem 1.
Do you have questions not on Theorem 1?
I do not have any questions.
Okay. I feel like your dad's...
What is next?
Okay. Theorem 2. This is what I wanted to argue. So I'm going to eventually make the argument that if you have functions that are not analytic, then roughly speaking, integration is supposed to move you up the scale of niceness, and differentiation is supposed to move you down. So in some sense, they're opposites. So the first thing to prove, this statement has more implications than what I'm saying right here. This is just the first weakest version of that statement that might make sense. So suppose you're like on the bottom of the scale, you don't have any nice properties except integrable. You don't even need to be continuous. The Theorem 2 claim is that if f is integrable, he has the bottom possible property of niceness, integrable on a to b, and you define his integral, f of x, by integrating up to x, then his integral is continuous. So the integral has the next niceness property. Okay, so we should prove this. The proof goes as follows. You pick a point C in this interval a to b. We're going to try to prove that the limit as x approaches c of f of x equals f of c. So this is what we're going to prove. I should write want. This is what we want. Because if we prove that this is true for any c in a to b, then we've proven continuity. So let's try to prove that. First, we notice that way back when we defined the integral, right? When I defined what it means for a function to be integrable, I put in by hand this sentence that it must be bounded, right? So we're not defining integrals of unbounded functions yet. So since we've assumed f is integrable here, by our definition of integrable, that means f is bounded. And the definition of bounded is simply that there exists a real number capital M with the property that the absolute value of f is always less than or equal to m on this interval. Right, if this were not true, if there were no such m, then that would mean that f gets arbitrarily large, like tangent near, pi over 2 or something. So we're assuming that's not the case. So anyway, fine, pick such an m. Now I'm going to explicitly calculate the limit as x goes to c of f of x. And to do this, it turns out to be useful to break it up. So here's c. We're going to break it up into considering points a little bit to the right of c, since this limit is really, the limit as h goes to 0 of c plus h for x. So I'm going to split it up into the case where h is positive, so you're to the right of c, and the case where h is negative, so you're to the left of c. So they're a little different. Let's do the h positive case. So we're going to try to bound, I guess, this difference between the value of f at c plus h and the value of f at c. So the first thing to notice is using the definition of this function as an integral, we just write the difference of those two outputs. So this is the first guy, f of c plus h. By definition, you just plug in the argument as the top bound of integration. And the difference with f of c is what you get by subtracting off this guy with the bound being c. And there's this nice thing we proved from the, what did I call it, the compounding theorem last time or something, that what we can do is we add and switch the bounds of integration, right? So if you switch the bounds of integration, you pick up a minus sign. And then the compounding theorem tells us that if we go from c up to a, and then from a up to c plus h, that's the same as going from c up to c plus h. So that's just algebra and some definitions. I put a picture to make it a little more intuitive, but this is the difference. F of c plus h. F of c plus h is all of the area up to c plus h. Maybe I should have put another picture here with a. So if you take all the area up to c plus h and subtract off all the area up to c, you're left with the area between c and c plus h. And this is the thing that we're going to try to bound this to show that this guy's continuous. But before doing that, questions on this manipulation we're doing so far?
I have no questions about this, as you quote it, manipulation.
Okay, good.
Though may,
Yeah.
On a totally unrelated comment, thank God I have good soda, because if I drank even one can of soda today, I'd be at 250 grams of carbohydrates.
Oh my God, don't die. Jesus.
I'm already at 200, and I have nothing out of the norm.
You eat a lot of bread. Those sandwiches, eating a lot of grilled cheese sandwiches is not going to help with if you want facial clarity.
Yeah, 4 out of the 6 things I've had today is bread and bread products.
Yeah, replace those bread with produce. You should be eating vegetables and stuff. Like that's.
Yeah. My God.
Yeah, that bread is not going to help with headaches and all this stuff. You're going to become insulin resistant, which will give you a lot of bad headaches and eventually diabetes. So it's not good.
Huh. Okay.
Good. Okay, so now let's use this boundedness assumption, right? So this is where we're using theorem 1, which I forgot to name, because recall in this proof we have a number capital M such that the absolute value of f of x is always less than or equal to that. So in other words, we could write this in two ways. F of x is always greater than or equal to minus m and less than or equal to capital M, right? So that is exactly of the form that we had in theorem 1, which I forgot to label, that if f lies between two guys, then his integral lies between those guys times the width of the interval. Right, so now I'm just going to use that with capital M and minus capital M, because that's what we have here. So indeed, just plugging in, the width of this interval from c to c plus h is h, of course. So the integral on that tiny strip up to h from c lies between capital M times h and minus capital M times h. And now I'm just replacing this integral with what we had on the previous slide. So I drew this nice picture to convince you that the integral, oh my God, why didn't you yell at me? Not integral of h, integral of f. There we go. Function is f. Should have yelled at me. Okay, so the integral from c up to c plus h of f is this thing, this difference between those two. So have to go and hide my shame that I wrote h. So anyway, this integral is the same as the difference of these two capital F functions. So that gives us bound 1. I'm going to call that equation 1. Now let's just repeat the same analysis when h is negative. So I won't go through all the details again because it's very similar, but the point is that if h is negative, so you're looking at a point slightly to the left of c, the point at which we want to show f is continuous, then f of c plus h, so this will be less than c, right? Because h is negative. Add a negative number to c. So f of c plus h minus f of c, this is the integral from c up to c plus h of f, but again, notice that this guy is less than c. So this is a backwards integral, right, from a higher number to a lower number. So we just switch the bounds using our thing from last time, that's minus the right order. And now with the right order integral, we again apply theorem 1 to bound this guy between, again, here we have to have the positive number on the right has a minus sign in front of it, minus m times h, because h is negative, right? So it's a little tricky. This is why we had to split it into two cases, because the signs are going to affect the inequalities. So now I take this inequality and multiply all three of the pieces by minus 1. And as you recall, multiplying by negative numbers flips the direction, right? So I did two things, which is kind of confusing. I both flipped the direction of the inequalities, and I also reversed the order in which I wrote it, I think, if I did it correctly. Maybe I did this wrong, actually. Let's see, I was supposed to multiply by minus 1, which I think I did do it wrong. I should have multiplied by minus 1. Yeah, I think I was lazy and didn't change the inequalities. So if I did it correctly, the inequality should look like this, which would mean, oh no, it's right. Yeah, just read it left to right. There we go. Okay, good, good. So this is correct. Wow, I had low faith in myself. So reading this top line from right to left, m times h is less than or equal to minus this integral. Minus this integral is indeed f of c plus h minus f of c, because you switch the bounds again. And then that's less than or equal to, going right to left, minus mh. Right? So this line going to this line is multiplying by minus 1, and then reading in the opposite order. Okay, just algebra, but are you happy with the arguments for the bounds in equations 1 and 2?
Yes.
Good. So we have two bounds now. Now let's squeeze. Notice these guys are two pieces of an absolute value inequality, right? Because they both bound this quantity, f of c plus h minus f of c, between here when h is positive, m times h, and here when h is negative, m times h. But we have a very nice function which takes in an expression like of the form m times h, and gives you a plus sign when h is positive and gives you a minus sign when h is negative. That function is called the absolute value function, right? If h is positive, this returns positive h, and if h is negative, this returns negative h. So we have massaged this into the form of an absolute value inequality by doing this minus 1 chicanery. So those are the two halves of that absolute value inequality written like this. M is positive, by the way, we chose that, so he can pop out of the absolute value. And now we're basically done. So recall, after all of these tricks, what we were trying to do is prove that f is continuous. What do I need to do to show it's continuous? Well, I pick a point c, and I show the limit as x approaches c of capital F of x equals capital F of c. Well, to do that, I have to, do some epsilons, but it's actually very easy now because we have this bound. So suppose someone comes along and hands you an epsilon. You just pick your h. Since I can pick to restrict to any interval I like, this h is, I should have called it delta, I guess, to remind us of the usual delta epsilon proofs. So maybe I should choose delta equals absolute value of h to be smaller than epsilon over m. Yeah, maybe I should have said that. Because if that delta is less than epsilon over m, that means all of your points are going to be within that distance of c, which we've just chosen means that, or as we've just proven, means that they're going to be bounded by m times absolute value of h, which will now be less than m times, well, absolute value of h is less than epsilon over m, so these things cancel, and the output values are within distance epsilon, which is exactly what we needed, right? This is, why did I put less than equal to? This is strictly less than. So this is the definition. Definition of continuity. Definition of conti. Okay, so that has proven now the limit as h goes to 0 of f of c plus h equals f of c. So any integrated function, any function which gives you the area under an integrable curve, is continuous everywhere, basically. Good. So integrating moves you up from integrable to continuous. Good, good. Thoughts on this?
I don't see how you can get much more important than what you did here.
Was that sarcasm? Or do you actually find this important?
That's not sarcasm.
Okay, good. I wasn't sure. It's hard for me to tell because I find it extremely important, but it's hard for me to tell what other people find important. Yes, good. So, well, I agree, but can you elaborate on why you agree that it is important?
Why do I think it is important? Oh god, that's a good question.
Well, yeah, if you think something, you should have reasons for thinking it.
Well, my mildly BS reason is because this connects two things that we've been learning about for the past 10 months.
Yes, true. That's one. Yeah, it's good to see the relationship between the different pieces of the puzzle that we're building here, the calculus puzzle. So, yeah, let's comment on that. So, what have we done? So we've studied continuity, and then we studied differentiability, which is taking derivatives. And then I'm not drawing this in the order of niceness. I'm drawing this in the order. Did I write too many? Differentiability. That's correct. And then we studied integrability.
Wow.
So this is not
Integrability? Integrability.
Integrability. Man, there's too many letters there. So, indeed, so this seems very important because continuity is the bedrock foundation of calculus. So one should understand how every new thing we introduce relates back to that. And now we see that integration is a very powerful tool for creating continuous functions. As you've seen, continuous functions have very beautiful properties. Right, they achieve their upper bounds on any closed interval. They have an intermediate value theorem, which is extraordinarily overpowered. So you could have asked, why are we introducing this integration thing that seems very abstruse? Well, we like these. We like these. So if you like these, you might say, do we have a tool for making more of them? Right, I want more continuous functions, and the answer is yes. As you started to see in Python, we can build new functions by taking integrals of familiar functions. So this gives us a handy toolkit for building nice continuous functions with properties that we enjoy that we haven't seen before. And I'll show you an example of that. Another reason why this is extraordinarily important is that it suggests, since this is connected to continuity, which as we already know is related to differentiability, it suggests a connection between an integral and a derivative. So this very naturally begs the question, okay, if integrating makes something more continuous, what is the relationship between an integral and a derivative? What should this question mark be? So I think that's also extremely important. Do you have other reasons why this result seems important to you? Because I also like it.
Okay, that water jet is annoying. I do not have any other reasoning behind my thought.
Okay. Good. Let's move forward then. So this is the main event, which I attempted to tease in that last comment about the relationship between integrability and differentiability, or integrals and derivatives. So as we'll see, that is exactly the question which is answered totally and precisely by the fundamental theorem of calculus. So here's the question we would like to answer. Start with a function f, lowercase f. Define a new function. For this slide, I'm going to call it a instead of capital F, just for this slide, to emphasize that it's an area. But this is the same thing as what we were calling capital F a moment ago. I just want to use the geometrical picture. So anyway, this a of x means start at some point lowercase a, find the area under your old function lowercase f from a up to x. Now our goal is to understand what happens if you take the derivative. First of all, is it even differentiable? Who knows? We know that if you integrate some guy, you get something continuous. We don't know if you get something differentiable. So we should think about that. And before thinking very precisely and carefully about it, let's get some intuition. So the intuition is that, well, what's the derivative? What's the derivative of this guy? Well, we know what that is. A prime of x, by definition, of derivative is the limit as h goes to 0 of a of maybe some point x I've called here, x plus h, minus a of x over h. Okay, so if we want to answer this question, we better come up with some way of calculating the numerator here, right? What's a of x plus h minus a of x? So, all right, I've drawn a nice picture for you here, and I'll ask you to walk me through the process. If we want to estimate a of x plus h minus a of h using this diagram, what quantity should I write down and why?
The water jet turned on right as you asked the question.
Oh no, I apologize. I was saying, if we want to use this figure here to get an estimate for the difference in this numerator, a of x plus h minus a of x, so take a look at this diagram and tell me what figure or what part of this diagram represents the quantity we want, and then what number is that equal to?
It seems that you've written down... What? I totally missed the question again. How did I do this?
Okay, so just look at the diagram and tell me what you see. Explain to me what I've drawn here. First of all, let's just understand the picture.
You have some... Oh my god, that thing again. Okay. You have some air quotes random function that is the integral of some other function f from a to x.
Yeah, good. So you say this blue part, for instance, this is the integral from a to x of f, right? So by definition, that's capital A of x. So the blue part is a of x. Okay?
Okay. You have written down f itself.
Yeah.
Okay.
Yeah. This blue curve at the top is the old function f, right?
Okay.
Okay, so you've explained what a of h is, so what part of this diagram is a of x plus h?
A of x plus h is going to be the right dotted bar.
Right dotted bar. So the red part?
Okay. It is going to be the area between a and x plus h, I believe.
Yeah, so it's the whole thing here, right? So this is a of x plus h.
Right.
Okay, so we're trying to find the difference between those. So if I take a of x plus h and subtract a of x, what part of the figure gives me that difference?
I did not understand the question.
If I take the difference, a of x plus h minus a of x, what part of this picture gives me that difference?
Well, the area you labeled orange.
Yeah, good. So this thin rectangle to the right. Okay. Now tell me what that area is approximately. What is this equal to?
I believe that this area is going to be the integral of f on the interval x to x plus h.
Good. Okay. So now approximate that. This is roughly a rectangle, so perhaps we ignore this excess at the top. If we do that, what is this area, the integral given by, or the area that you just described by an integral, what is that equal to?
I believe that this is going to be f of x times x plus h minus x, or just h.
Yeah, minus x, so these guys cancel. So yeah, it's just a rectangle, roughly, if you ignore the excess, it's a rectangle with width h and height f of x, right? So this is f of x times h. Very good. Okay, so now how do I manipulate this thing, which you've just told me that a of x plus h minus a of x equals f of x times h? How do I manipulate that to look like the definition of the derivative?
Here I go muting myself again.
So how do I use the thing you just told me to compute the pink expression?
Oh, we can divide out h on each side.
Good. So it looks like f of x is a of x plus h minus a of x over h. Okay, so this isn't a proof, but this suggests a guess, a natural guess for what the derivative of capital A of x is. What is that guess?
I totally missed the question again.
I said, what is the guess suggested by this equation? If you were asked to guess what is a prime of x, what does this equation suggest that that guess should be?
A prime of x seems to be equal to f prime of x.
F prime or f?
Wait, let's see. Oh. Oh, yeah, I guess it is f.
Looks like f, right? If we could just take the limit as h goes to 0 of the right side, the left side is just f, right? So this seems to suggest... What do you say?
You could take the limit of the left side, and it would just automatically not be a limit because h is not on the left side.
Right, yeah. So, yeah, the left side is unaffected by taking this limit. The only step where we've been sketchy is with this approximation, where we've dropped the excess. But, right, at this step, I agree. You could take the limit on both sides, and this would tell you that the derivative of the area function is the old function, lowercase f of x itself. But if you think about it, that actually isn't so crazy, because what is the derivative? The derivative is telling you how fast is the area function changing if I change its input a little bit. What is its input? Its input is basically the width of the rectangles I'm adding up. So the derivative a prime of x is just asking how fast is basically area equals, I'm going to use h for height times width, changing as I vary the width w, right? Because the area is simply changing the width of the rectangles that you're adding up. And the natural answer is that, well, if you, what is the slope, right? What is the slope of a when I change w? Clearly, that slope is simply the height of the rectangles, but the height of these rectangles is controlled by the function value. So it's actually not so crazy that the calculation you just showed me suggests that the derivative of the area function is the original function whose curve we're finding the area under. Okay, so let me show that one more time, and this time I'll keep the excess in, just to show you, yeah, I used e for this. So the thing you told me a moment ago was that the area at x plus h minus the area at x is approximately f of x times h, right? This was the thing you just told me. It's just that the red rectangle has width h and height f of x. So the difference is given by this thing. So first comment, before we even start doing the limit argument, here's another way to see why this would tell you that the derivative of the area function is the original function. We're just going to rewrite this in a slightly more suggestive way. This is written a of x plus h equals a of x, I should say approximately equal to, a of x plus f of x times h. This looks oddly familiar. What technique that we've seen does this remind you of?
I wonder if it's a tangent line approximation.
It's precisely that. So we have this other approximation that g of x plus h, which I say on the next line, is approximately equal to g of x plus the derivative g prime of x times h. So this tangent line approximation, or this approximation to the area, would be a tangent line approximation if the two derivatives here matched, which is to say that if f were the derivative of a. Okay, so that's one way to see it. The other way to see it is to explicitly write down the excess, right? So by excess I mean I'm going to replace this approximately equal to by an exactly equal to. that a of x plus h minus a of x is this thing plus some excess, which I call e of xh, and which is probably hard to calculate. I'm just going to keep it in to see what happens. So if we do that, then solving for f of x and taking the limit, we have f is the limit as h goes to 0 of this thing, which we got a moment ago, which defines the derivative of a, minus the excess as a function of x and h over h. So if we had a reason why this thing went to 0, so if this thing vanished, does this go to 0? Which seems reasonable, just geometrically, looking at the picture, that that excess would get smaller and smaller as you reduce h, and it's also suppressed by an h in the denominator, so you have to be a little careful. But if that were true, then indeed, we would know that the derivative of the area function is the original function itself. And here I'm just repeating that how quickly the area changes as you change the width is the height, which is f of x. So it's all very sensible. Okay, questions about this intuition? I would like this to be painfully clear before moving on. So ask questions if you have them.
I do not have any questions.
Okay. Good, good. All right, so this suggests a guess, which I will now prove for you. So this is it. This is the first fundamental theorem of calculus. Let f be any integrable function on an interval from a to b. As we've proven, if you have such an integrable function, he's guaranteed to be continuous, so you might ask, is he differentiable? Well, let's see. If we define a function capital F on the interval from a to b by integrating this guy, which we know we can do because he's integrable, then, as it turns out, we don't actually know that this guy is differentiable. So we're going to make an additional assumption. We need an additional assumption. You need to assume not only that f is integrable, but that lowercase f is also continuous at some point c in a to b. So I want to emphasize, not every integral is differentiable. But under these assumptions, if f is continuous at a point c, then we know that the area function capital F is differentiable, and that its derivative equals the original function. Okay, so I'll prove this in a moment, but just a remark. If you ignore all of the important stipulations I just made about continuity, what is this roughly saying? This is roughly saying that derivative and integral act roughly like inverse operations, right? If you integrate from a up to x, and then take the derivative, and you have these nice continuity assumptions, then these things kind of cancel in some sense, and you're left with the original function, is one way to think about it.
Random thought about your theorem, I guess.
Okay, what's the thought?
It kind of looks like it might be saying that continuity implies differentiability.
No, continuity of a function implies differentiability of that function's integral. Different function.
Okay.
Yeah, be very careful.
Okay.
Yeah, so
That makes more sense.
just to emphasize how this connects with what we did before. So let's have integrable, continuous, and then differentiable, right? So differentiable. So we know that if you know a function is integrable, then its integral is continuous. What is this saying? This is saying if the function is continuous, then its integral is differentiable. So you could think of this as another version of the integration increases niceness proof, right? The first thing we proved is if you start with integrable, you take an area, then you're continuous. This theorem tells you if you start continuous, take an integrable, you start continuous, you take an integral, then you're differentiable. But this theorem is even stronger. It doesn't just tell you you're differentiable, it tells you what the derivative is. And it's a very nice answer. It's just the original function. So indeed, it's good to be clear that these are different functions. But anyway, that's a very good comment. Other thoughts on the theorem?
I have no thoughts.
Okay. It sounded like you smirked at the end of that sentence, but okay.
Wait, how can that sound like a smirk?
You can tell people's facial expressions by the way their voice changes, right? Or did I misinfer?
You did not misinfer.
Okay,
I'm scared.
good. I have eyes everywhere. Um, okay, good. This is the most important thing that we're going to prove, so I'm going to actually ask you to do part of the proof to make sure you understand it. So what I'm going to do is say, well, notice that this theorem is supposed to go through and work if C is any point in a closed interval. In particular, C could be one of the endpoints. So what I'm going to do is I'm going to prove it when it's not one of the endpoints. I'll prove it for when C is in the open interval. It's also true for the endpoints, but to prove it at the endpoints, you need to repeat the proof and change some things, right? You have to change, because when you're at an endpoint, you only have one-sided limits, right? Limits from above or below. You only have right and left-handed derivatives, because you can only approach from one side. So you'll have to write out all those steps with the appropriate changes of this proof. So you'll do that in a DC. And I think it's very important, because if you don't understand why the fundamental theorem of calculus is true, then you've kind of wasted your entire time spent learning calculus. What was the fucking point? So, okay, I'll prove it for this case now. Anyway, so what are we trying to prove? We're trying to prove that f is differentiable and its derivative is lowercase f. Right, so first we write down the definition of the derivative. F prime of c is the limit as h goes to 0 of f of c plus h minus f of c over h. As before, it will be useful to split up into positive and negative h's, just because areas work differently if you're moving to the right or to the left. So let's start with the positive h case. We want to balance numerator in some way. So we should write down what the numerator is. Indeed, the numerator is the integral from c up to c plus h of f, by definition, right? Because f, capital F, is the integral from a to some point x of little f, right? So this is the integral up to c plus h. This is the integral up to c by the compounding thing. This is the integral from c up to c plus h. Okay, now, since this is expressed in terms of an integral, the only way we know how to compute the value of an integral right now is to use upper and lower sums. So first let me go to the picture. Again, we're in the h positive case, which means we're to the right of c. So I'm just going to define lowercase m sub h and capital M sub h in the following way. You pretend this is a partition and do what we did before. You basically find the infimum of the function on the partition, or the subpartition or something, and find the supremum of the function on that interval. But since this is, I'm not calling this m sub I and m sub I, because when we were in the partition case, I told you which subinterval you're in. I'm going to call them lowercase m sub h and capital M sub h, because they're indexed by h, which is how far to the right of c we are. So it's almost the same thing, just a slightly different notation. So in math, what did I just say? I said lowercase m sub h is the infimum of f on this interval from c to c plus h. Capital M is the sup on that same interval. Okay, fine. Not rocket science, just taking suprema and infima. But why is that useful? Aha! You will ask again probably why I proved this very silly theorem. Theorem 1 I was supposed to call it, that if you have an upper and lower bound of an integrable function on some interval, then you can bound its integral by those bounds on either side. So now we have, in the same notation, lowercase m sub h and capital M sub h, two bounds to which we can immediately apply that theorem. So I'll do that, and that tells us, well, the integral from c to c plus h must lie between the sup times the width and the inf times the width. Has to lie between those. Now I just do some algebra, divide through by h everywhere in this inequality. Now you see why I split it into positive and negative h again, because if h were negative, this would flip the signs of inequalities. So this middle part is now the integral from c up to c plus h of f over h, but of course this thing is simply capital F at c plus h minus capital F at c, as we saw in the previous slide. So we've got this first result. Okay, so that's, maybe I should call that 1 or something. So that's the main result in the positive case. Next I'll go through the h negative case and do the same work, but before I do that I should ask if you have questions about the positive argument.
I do not have any questions, but I would like if you slow down by like 5%.
Slow down to 5% of how fast I'm going now, so
like
1/20th?
From 100% to 95.
Oh, okay, good.
Speaking just a little quick.
Sorry, I'm getting excited. Okay, so we're happy with this when h is positive. So now I need to repeat these arguments and be careful about flipping the signs of inequalities when h is negative, or 0, in fact. But the 0 case is very simple because there's only a single point in each of these intervals. So let's do h negative. The picture is almost the same, except now you should think of this being mirrored, so we're kind of looking at the other side now. When h is negative, we're over here, and I still take the inf and the sup. I should call that m sub h, sorry. So I do the same thing and take the inf and sup of the function on the interval from c plus h, that should be c plus h up to c, when c is negative. So now h is lying, your endpoint is to the left. So I do that, as before, find the lowercase m and capital M. And now, we saw something similar to this in the previous proof. I can again apply Theorem 1 to get a bound for this integral, but now I have to be careful because negative h is the positive number, so this is the bound on the right side, and similarly, yeah, well, they're both positive, I guess, but this is a smaller positive number is the point. Smaller positive. Right, because capital M is larger than lowercase m. So this is our bound on the value of the integral when h is negative. Now by similar reasoning to in the positive case, this difference, f of c plus h minus f of c, which is the integral from c up to c plus h, which is again smaller than c in this case, we can reverse the bounds of integration and pick up a minus sign, as we've seen, or as we've defined, really. So now this is from the leftmost point to the rightmost point, as it should be. And then this gives us, just going from here to here, I've kept, I think, yeah, so I multiplied through by minus 1, and then plugged in this integral for the f stuff. Right, so I'm going from here to here, I multiplied by minus 1 in the left side, which kills off this minus to a plus. I reversed the sign of the inequalities. This is now a greater than or equal to. In the middle piece, I wrote this integral like this with a minus sign. And then, since I multiplied by minus 1, that got turned into a plus. So that gives me the middle piece. And on the right, again, reversing the sign of this inequality and flipping this minus to a plus. So it's just taking the bound from Theorem 1, multiplying by minus 1. Oh wait, I didn't do that. I did that in this one. What did I do? This is the same thing. Oh, I made an editing error. I was supposed to have an intermediate step here before I multiplied by minus 1, and then I edited both of them instead of just editing one of them. These are the same equation, but they should not be. Okay, that's a whoops, but well, whatever. I think you can follow if I do two steps at once. First, imagine plugging in the integral so that this is negative here, and then imagine multiplying by minus 1 to flip the signs and clear the minus signs. Okay, well, whatever. So now we have two different inequalities that bound this guy when h is positive or negative, right? So this thing, again, I could divide by h. No, I didn't divide by h. I'm confusing myself. I multiplied by minus 1, but I should have divided by h again. So when I divide by h, which is negative, that's the skip step here, it should be like this, c plus h minus f of c less than or equal to m sub h. Now this is all over c, or h. There we go. So this is what happens when you divide and reverse them again. But the point is that this is the same inequality we got when h is positive. So we have this inequality which works when h is positive and when h is negative. So now we just need to use this to show that the limit of the middle piece, this is what we want. Want the limit as h goes to 0. And then we can apply the squeeze theorem, because we have an inequality which is true when h is positive or negative, so it's true on both sides. Well, if we're going to squeeze, we should probably know what the two guys on the left and right do as h go to 0 to make sure we are squeezing the intermediate term or expression between those limiting values. But we know that both of those are going to go to f of c because f is continuous, lowercase f is continuous. So why is that true? Let's go to the picture. So if this guy is f, and lowercase m and capital M are the sup and inf of f on the interval h, then as I take h smaller and smaller, as I take h maybe smaller than some delta, then I know that all of the function values between c and c plus h, or even on the left side as well, I know that all of them are going to lie between whatever epsilon bars I choose, because f is continuous. But the statement that they lie between epsilon bars, that I can make as small as I want, means that both lowercase m and capital M must get as close to f of c as I want. Right? This is just the definition of continuity, that you can make all of the function values on an interval, including the sup and inf, very, very close to the function value itself by taking h or delta very small. So this is why we needed to assume that the original function f is continuous in order to get this squeeze argument. So if you buy that, then by the squeezing argument, the lowercase m is going to f of c, the capital M is also going to f of c, and we know that f satisfies this inequality, so he gets squeezed when I take the limit as h goes to 0, this whole thing. Well, this guy goes to f of c by continuity, this guy goes to f of c by continuity, and this thing in the limit is the definition of f prime at c. So it's very good that we proved the squeeze theorem, or actually I think you proved it, CD2 or something. But anyway, the squeeze theorem tells us that the derivative of this integral function, capital F, is the original function, lowercase f, at that point c. Good. Important result. The first version of the important result. So, good. Questions on this proof?
I do not have any questions due to the importance of this. I assume you're recording, right?
I fucking hope so. Let's see. Yes, I remember this.
Yes. Due to the importance of this, I'm likely going to want to review and write this down myself. I don't know why I want to do that. It's just a thing I feel I need to do.
I think that's very important. Yeah, that's why in a DC I'm asking you to basically rewrite the whole proof and just make small changes, right? When there's these things. So you can write this version as well if you like, and I'll try to correct this typo because I should have left the minus signs in, then divided by h and got rid of them that way, but I screwed this up. But yeah, you should understand how this works. You should understand how the proof of the second one works as well.
I think the most amusing part of all the proofs that we've done in this meeting so far is the dividing by h to get some other function.
Dividing by h to get some function. What do you mean? Like these steps with the flipping the inequalities when we divide by h?
Yeah.
Yeah. This
or just the center limit. It just seems to be the most.
Oh, you're cutting out a little bit, but I think you were saying about using h to get the center thing to limit somewhere is very common. Is that what you were saying?
Yeah.
Okay. Yeah. It comes up a lot with integrals to do that, just because, I mean, all we're trying to do is convert a statement about areas to a statement about the function itself. So basically every time you prove something about this, you just consider a little bit to the right, h positive, consider a bit a little to the left, h negative, and get some bound. And yeah, it's kind of cute technique. Okay, I think I have a challenge now. Okay, good. So what did we prove? We proved that if capital F of x, man, there's a typo here already. So I should ask you what g prime of x is. Anyway, so what did we prove? We proved that if capital F of x is the integral from a up to x of f, then ddx of f is lowercase f. What happens if I switch the bounds? So instead I define a function g, which you plug in x not to the upper bound but the lower bound of integration and go up to some fixed point b. And now I take the derivative of that guy. So what do you think this should be?
Remind me. Lower. Are we talking when we say lower limit of integration?
So we're just talking about the left and right endpoints, right? So this guy would be from x up to b. This thing would give you the area g of x under the function f.
Oh, that was the answer
No,
to my
you.
question.
Oh, well, maybe I misunderstood. You were asking what is meant by upper and lower bounds of integration, and is this the answer that you were
Well,
asking?
lower integration. Oh,
Wait, ask your question again because I don't think I understood it.
I see what you're saying. You know, smaller. Well, this is the thing that is changing here. It is going to be moving to the right closer to B, and therefore the area is going to go to 0 as x approaches B. This is just exploration.
Oh wait, so you just said that this function is going to go to 0, so the area function as x goes to b should be 0. That was the claim you just made?
I believe so.
Okay, good. So that's true. Yeah, that's true. And we knew that because we defined last time that the integral on any single point domain from b to b, that integral of any function is always 0. So good. That's correct. So we know that.
It's only exploration, but
Yeah, good. So okay, so now how can we use what we know about integrals and the previous fundamental theorem to find the derivative, g prime?
I've been muted.
Actually, the audio quality keeps cutting in and out, and I'm like missing a lot of messages. So let me just try to leave the call and come back and see if that makes it any better. It's hard to understand at the moment.
No, I was muted.
No, even when you were unmuted, I couldn't understand what you were saying. So hold on, let me try this.
See, the video is breaking. You don't need.
I'm just gonna reduce the frame rate and quality and see if that helps.
Well, reducing the quality makes it hard to see.
Oh, okay. Well, maybe I shouldn't do that then. Okay, so all right. Well, fine. I'll keep this and hope that I'm able to understand you. But yeah, it's not that you're muting yourself. It's that when you speak, it sounds like blum, bleh, duh, duh,
Oh,
you know, when
God.
it gets very robotic for some reason.
That is weird.
Okay.
All right.
What's this?
So, using the stuff that we have, well, no, not quite. I believe in a case where we would have, okay, this is probably a lot simpler. I'm finding this lower limit equaling x to be the strangest thing.
Yeah, it's different from the upper limit. Now we're saying if you change x, so first of all, I mean, if the function's positive, let me ask a simpler question. So if the function's positive, do you expect this derivative to be positive or negative? Or in other words, if I move x a little bit to the right, do I expect the area to go up or down?
I would expect the area to go up.
So if I move x to the right, you think that now this green area is bigger than the pink area.
Oh, wait. In a normal... Okay. No, the area would get smaller.
Good, good. So, right, in the old case, if it were the other way, so this was a and x, in the old case, when it was the upper bound, then when I move x to the right, the area gets bigger. But in the case we're considering here, x is the left endpoint, so if I move to the right and the function's positive, the area gets smaller. Okay, so that's useful, but how can we use that to find the derivative? Maybe it would help, I will give you a hint, maybe it would help to just put in an extra point A on the left. You could fix any constant point A that you like. Now, do you see how you could write an equation involving the integrals from a to x and x to b, which might make this a bit easier?
Yes, I can. So I believe we can represent our ordeal here as, well, the integral on x to b of f is equal to the integral of a to b minus a to x.
Yeah, that looks good.
Omitting the f here, just,
yeah.
I don't know.
That's fine. Okay, so now we should, since we're trying to find the derivative, and this is g, maybe we should just take the derivative of both sides of this equation, since we're just trying to get an idea for the answer, right? So what happens if I differentiate both sides?
So I believe that the integral from, well, pardon me, the integral from a to b of f is going to be a constant and therefore 0.
Good, so its derivative is 0. Good.
Right. And I believe by the fundamental theorem of calculus that we're going to have that the integral from a to x of f is going to be equal to f.
Careful, you don't use the word equal to mean differentiates too, right? So the integral from
Right.
a to x of f is not equal to f, but its derivative is equal to f. Good. Okay, and then what's left over here?
And on the left side, well, equals g.
Well, let's see. It's g prime, right? Because we're taking the derivative. Good. So
g prime equals negative f.
Right. Okay. So g prime of x equals minus f. So this is kind of a backwards fundamental theorem of calculus that if the thing which is changing is the left endpoint rather than the right endpoint, then when you take the derivative, you actually get minus the original function back. Now there's actually a kind of hacky way to see this, which isn't totally correct, but you could have said the following. G of x is minus the integral, you just put in a minus sign and flip the bounds of integration, minus b up to x of f, and then apply the fundamental theorem to this equation, and say, well, now the bound is up in the top, right? So now I can just do this, and it should be minus f. So this argument isn't actually correct, because you can't apply the fundamental theorem to conclude that, because we only proved the fundamental theorem when these two bounds were in the right order, right? Right now they're in the wrong order, because b is to the right of x, apparently, from the way that it's written. So this is incorrect reasoning. This is 0 out of 10 points if someone said this, but it happens to give the right answer. Okay, but good. I think we understand the right answer with the right reasons now, which is split up the interval and then apply FTC after differentiating both sides. Right. So as you said, g of x, which is from x up to b integrating f, can be split up into the constant integral from a to b minus the integral from a to x. Differentiate, apply FTC. You have answered the challenge, because I was going to ask why this is 0, because another common mistake people make is say, d dx integral from a to b of f. Oh, derivative cancels integral, so this is f, right? No. If this were x, as you know, the answer is f. If this is a, then you're differentiating a constant which knows nothing about x, independent of x. This guy sees nothing. So it's good that you notice this. Another reason why people sometimes make this mistake is because they use that other notation which you really shouldn't if you shouldn't use the same letter if you're going to use that notation. People will sometimes make this mistake. They'll say, all right, I can use this notation for the integral, f of x dx, and now I take d dx, and then they think, oh, well, maybe this moves under the integral or something, f prime of x dx, right? That's obviously a falsehood. You should not use the same dummy variable in the integral as that you're differentiating with respect to. So this is why you've seen on DCs I usually put a t or something else in here so that we don't have a conflict. But anyway, these are just things to watch out for. Okay, questions about the backwards FTC?
If this is the backwards FTC, then what is the second FTC?
The second FTC is a slightly stronger version. So this thing tells you if you have an integral and you take a derivative, you get the original function back. The second FTC is going to give you a more operational result, which says if you have a function and you know there's an f with this property, how do you calculate the value of the integral? So the second one actually gives you a procedure, so you can just write down the answer for the area without doing a lot of upper and lower sums. So we'll work on that shortly, but first, actually there's multiple versions of the second FTC. I'm going to ask you to do a weaker, this is the easier version. It's giving it as a challenge. So this is one way. Sometimes when people say second FTC, they mean this, but I don't. So anyway, so here's the challenge for you. Suppose I hand you a lowercase function, a function lowercase f, and I tell you that f I've just handed you happens to be a derivative. That f is the derivative of some function g. F is g prime. And now I ask you, what is the integral, what is the area under that function f from a to b? Okay, so you could read the hint and think about it for a moment, but how should I calculate that?
I don't know why that jet happens.
You need the headphones, man.
They're here somewhere.
You have over-ear ones?
I don't have any over-ear ones.
No, you see how, well, my video is probably too small, but see, I mean, this thing with the noise canceling mic and like nice, comfy, you need something like this.
Logitech something?
Well, the Logitech ones are cheap. This is a gaming headset I'm using, but you can get Logitech if you want to pinch pennies or something.
I know that my brother got like $60 ping wireless Logitech gaming headphones and those things.
Yeah, you should get something like that. $60 isn't that much.
Isn't that much?
It's just money.
Quotation. Let's see. So we proceed as the hint. We let f of x equal the integral of f from a to x. And then we take the derivative of each side and see that f prime equals f.
Prime of x equals f in particular, which is the same as g prime of x, right?
And that means that f prime of x equals, but we are in what is f on this interval. F on the, not sub, lowercase f on this interval.
I heard half of every word in that sentence because it keeps cutting in and out, so I understood none of it. Sorry.
Oh, great. Did you say sub?
I just heard C say sub. I don't know what that means.
Oh, God. I can hear my voice, and I don't like it.
It sounds a little clearer now. Okay, sorry for that. Could you say what you said one more time? I apologize.
Okay. Since capital F prime of x equals g prime of x, I don't know where to go from there. Let's see.
Well, it's kind of like, I mean, remember when we were doing accelerations and so forth? If you
If
have,
we let x equal b, then that does give us our answer that that equals f prime at b, or g prime at b, but
uh,
seem all that useful.
if we let x equal b, uh, I don't understand. So if we let f prime of b equals f of b equals g of b, so that doesn't tell us the integral. What we want is f of b, not f prime of b, right?
Hmm.
Right. I mean, you should think of this the way that we did when we were doing projectile motion and accelerations and so forth. So for instance, if you know you take two derivatives of some function and he's constant, then you can go backwards. You say, I take one, plus. I took two
I can't keep directions in line.
what, oh, I don't understand. You can't keep directions in line? What are you saying?
Thinking about what the anti-differentiation of f is, I say anti-differentiation because that's just okay. Never mind.
Okay, yeah, I wasn't sure what you were saying, but what I was trying to convince you of is that um, if we think of this the way that we did when we were anti-differentiating to solve differential equations, what we did was say, okay, well, to remove one derivative, for instance, if g is a constant, then I would tack on a function of time, and I would add some c. Because whenever you try to remove a derivative, you have to add a relative constant, right? Because the derivative would have killed that constant, and you would not have seen it in the integral. So I claim you could do something similar and say, okay, well, if f prime of x equals g prime of x, and I anti-differentiate both sides, then I know something about f and g. What do I know about f and g?
We know that we're talking about capital Fx itself and not what it is defined as. Oh, wait. So I believe that the anti-differentiation of g prime of x is... Okay, is that the right step?
Yeah, we're trying to anti-differentiate and get a relationship between capital F and G, right? So if
It seems...
what do you say?
I'm not silent, I'm just thinking.
Okay. Maybe a way that would make it easier. So let's think about it this way. I can write this as, if I take the derivative of f minus g, right, because derivative is linear, so I can just move g to the other side and say f prime minus g prime is the same as ddx of f minus g, of x, of course. That's 0. And I claim that you know how to anti-differentiate 0. If something has a derivative equal to 0, then what is true about that function?
Then they are equal.
No.
Then what was the question again?
If I take a derivative of a function and it equals 0, what must be true about that function?
It's horizontal.
So it's a constant, you're saying. Good, okay, yeah. So you say if I take the derivative of a number, of a function, and I get 0, then that thing must be a constant. So in other words, f of x is related to the function g of x by some constant, which we have to determine, right? So if two functions have equal derivatives, then they differ by a constant. Right? Good, okay, so now we just have to determine what is that constant. So let me erase. So we found that, capital F of x equals lowercase g of x plus some constant c. Okay, so now I think you had a good idea before for trying to figure out what this constant is when you're thinking about the behavior of this guy at the endpoints. So do you see a way that we could pin down what this function, or sorry, what the constant c is? How we could pin that down using the behavior of capital F at a or b, for instance?
Are you referring to my substituting b for x idea, or something?
So yeah,
Or
that gives us one thing. We know integral from a to b, if we put in the right endpoint b, that tells us that the integral from a to b of f is g of b plus c. So that's one thing, but we still don't know what the left side is. So do you see a different number that we can plug into f with the property that we know what its output is going to be?
we can plug in x equals a.
Good. So what is f of a in particular?
Capital F of a is going to be equal to 0.
Yeah, area under a point is 0. And that means if we're plugging in a for x everywhere, g of a plus c equals 0. Or in other words, the constant c that we were trying to find is minus g of a. Okay, good. So now let's finally answer the question. We're trying to answer the question, what is integral from a to b of f? Well, I claim we have all the... What do you say?
Is it g of x minus g of a, where we are simply substituting b equals x?
Yeah, good. So all I've done is taken this bottom line and put it in for c up here. So the answer is integral from a to b of f is g of b minus g of a. Okay, so this is one version of what people call the second fundamental theorem, because it gives you a very easy way to find what the area under a curve is. So let's just, we got lost in the weeds trying to prove that a bit, but let's just go back and see how we could use this. Right, so suppose I wanted to answer something like, what is the area under the function x raised to the power 7th dx, right? I just look at this theorem, and it tells me, okay, well, this is my function f. Is it true that f is the derivative of some function? Is it true that f is the derivative of some other function, maybe g, maybe like 1/8 x to the 8th? If you can find a function g with the property that g is differentiable, and its derivative is the f that you're integrating, then you know the answer immediately. All you have to do is write down g of b, which is 1, minus g of 0, which in this case, well, it's going to be 1/8 times 1 raised to the power 8 minus 1/8 times 0 raised to the power 8, which is of course 1/8. So this is why this theorem is extraordinarily powerful, because notice we have now a totally rigorous end-to-end proof. There was no sloppiness, no skip steps. The FTC was rigorous. We have a totally rigorous proof that the integral of this thing is 1/8 without using any lower or upper sums, without proving anything. If you wanted to prove this with the definition, you would have had, some lower and upper sums where you would have had a sum, you would have had, I don't know, probably b to the 8th over n to the, no. You'd have some b to the 8th times a sum from, I don't know, I equals 1 to n of I raised to the power 8, and you would have to prove by induction some theorem about the sum of things raised to the 8th power, and show that you can make the upper minus lower less than epsilon, and it's extraordinary amount of work, because that's just how the integral is defined. But the second FTC tells us that, well, if you can cook up an antiderivative, any function g, which differentiates to your integrand, which is f, then you just plug in top and bottom and subtract them. Very, very powerful. Okay, good. Thoughts on this?
No thoughts.
Okay, good. Alright, so let me try to dispel... Well, first I'll review this.
Oh boy, another... Oh wait, I thought it was another challenge.
No, it's same title, but just the solution. Good, indeed. So the solution that we just saw was f prime equals g prime. That means f is g plus a constant. Plug in a to find that c is minus g of a. That means f of x is g of x minus g of a. Plug in x equal b to conclude capital F of b, or the integral from a to b of f, is g of b minus g of a. Okay. Good. Notice that we had to assume. That f was the derivative of something, though. Okay, so let's prove what I like to call the second fundamental theorem. But first, I would like to immediately dispel some misconceptions. Because some people see this, and then they immediately think this now replaces in my head what I mean by integral. All of the upper and lower sums go away. They think the following very wrong thing. So I will label this a common misconception. If I had to pick one thing that people come away from a calculus course believing, which is wrong, I would pick this one. So if you learn nothing else from me about calculus, please learn that this is not correct. So if you ask someone in Mr. Spirk's calc class, they would probably say the following. The symbol integral from a up to b of f means you find a function g of x with the property that g prime of x equals f, and then compute the difference g of b minus g of a. Many people think this is the meaning or the definition of the integral, or the integral sign, or whatever. This is false. This is the result of a theorem which applies in some cases. You will recall that the definition, the thing which is meant by this symbol, is the supremum of all of the lower sums of f on a to b in partitions p, which must be equal to the infimum of all upper sums, again, in partitions from a to b. So,
but it's so easy to make it common core.
Yeah, exactly. That's why people get this misconception, because they are never asked questions about making partitions or implementing this in Python, so they see with their own hands and eyes how to build this and understand what this is doing. That's very hard to do in a common core way. So instead, this beautiful subject, one of the most astounding accomplishments that a human mind has ever produced, proving the fundamental theorem of calculus, this is reduced to nothing more than manual labor, drudgery, finding antiderivatives, plugging in numbers on a calculator and writing them down, which is an absolute shame. So I'm emphasizing this, and I would like to explain why this is a huge problem. I mean, you know it's a problem just because it's wrong, right? Here's the definition. This is not the definition. But you might think, okay, how bad could this be, right? They seem to agree in certain cases, so maybe it's okay if you forget the definition and think this. I would like to argue that it's actually never okay. So, reason one. We've seen many functions already in DCs and previous examples, especially in the continuity unit. We've seen many functions with the property that they are integrable, so you can compute the integral, but they are not the derivative of any function. So I'll think of a very simple-minded example. So here's a function f, which is 0 everywhere, and then pops up when x equals 1. It pops up to 1 at a single point, right? So here's a nice function f. Now, we proved before that moving the value of a function at one point does not change the value of the integral. So for instance, integral 0 to 2 of f equals 0. So a student who believes the very wrong thing from the previous slide would look at this and say, aha, to find this integral, I just look for an antiderivative. I look for a function g such that g prime equals f, and I evaluate it at 2 and at 0. So I'll ask you, here's the challenge. I guess I answered the first part in my excitement to tell you what the integral is. Well, the integral is 0. But I'll ask you, why do we know that there could never be such a function g whose derivative equals f? Why is that?
Because, let me think. It would seem that such a g would okay, good job, Self. There is no way to, I'm going to say anti-differentiate g and get that point?
Yeah, you're saying basically that you could never get a function whose slope jumps up to 1 at a single point and nowhere else, right? We would be looking for a function g whose slope is 0 in most places, so he's constant most of the time. Maybe it looks like this. Then at a single point, g has a slope 1, and then he goes back to being constant. How is that possible? the definition of slope requires you to compare, as you were telling Berna before, the values, not m, the values at nearby points. So for any reasonable, well-defined function, we actually proved this. You might remember this was something I proved, that derivatives cannot have point discontinuities if they exist and are continuous on an interval except possibly at that point. We proved this by L'Hopital's rule in Chapter 4. So I proved that under these very mild assumptions, that the derivative exists and is continuous on some open interval, except possibly at that point, it can never have a point discontinuity. Your slope cannot jump discontinuously. That's why I proved this, because it's important for understanding that there are integrable functions with no antiderivative, right? So that theorem we proved with L'Hopital is a very simple example of why there are functions whose areas you can find, but you could never use the fundamental theorem to get that area. You could only do it by using the upper and lower sums. There's no antiderivative. End of story. Okay, that's one reason. Reason two, you might say, okay, well, we know that if f is continuous, if we assume our original function was continuous and we take its integral, that thing, then we can differentiate that again, right? So that integral, capital F, apparently is differentiable. So what am I saying? I'm saying if f is continuous, then capital F, which is the integral from a up to x of lowercase f, this thing is apparently differentiable by the first fundamental theorem. So that means if we want to find some antiderivative, we could say, I don't know, g of x equals f of x, and then we would have g prime equals f prime, which is f. So you could say this. You could say, all right, fine. What if the function were continuous? That previous example you used wasn't continuous. So maybe you say, I only care about continuous functions. Now am I allowed to think of this symbol as asking for an antiderivative? But you can see this is circular logic, right? If you were a student saying this thing, I would like to interpret this as asking me to find an antiderivative and then, difference it at the endpoints. That doesn't make any sense, because we only know that this antiderivative exists because we built it by using upper and lower sums, right? We built this up by hand. We built what it means to take an integral. So we had to use all of the technology partitions to show that there exists an antiderivative. So you can't say this just means find an antiderivative, I don't need to know about partitions, because you needed partitions explicitly to get that antiderivative. Without that, the definition, the fake definition that students might give, which I showed on the previous slide, this thing is not only wrong, but it's useless, because you would never know how to rigorously get such an antiderivative if you didn't know what partitions were. Last thing. So in future meetings, I'm going to retcon. I'm going to change all of our definitions of common functions. So before I defined e to the x in this very sloppy way, where I said here's this sloppy definition involving, some number e, which I didn't really define properly, and then I defined the log is the inverse of that sloppy definition. So that was not at all rigorous. This is what we're going to do. I'll preview it for you right now. Here's the new definition, which I'm going to retcon the sloppy shit to. This is totally rigorous. Definition. Function log of x is the integral from 1 up to x of the function 1 over t dt. This is totally rigorous. All I needed to define this was to know how to add and multiply numbers, right? You take lower and upper sums, you multiply the infima by the widths, you multiply the suprema by the widths, and then you just had to know how to take sup and inf. So if you have defined addition, multiplication, sup, and inf, which we've done, then this thing gives a totally rigorous definition of the log function. That's it. We define log this way, we define e to the x as the inverse of this, and in particular this gives us a totally rigorous definition of the number e. None of this limit 1 plus 1 over x, x goes to infinity, raise the whole thing to the power x, none of that bullshit. This thing is the unique number such that the integral from 1 up to e 1 over t dt equals 1. You can prove there's only one number with this property, that defines e. And as you saw, you plug this into Python, you got a 1, that's what defines e. Alright, maybe you say, fine, I don't care about defining things I already understand in terms of this complicated new integral thing, I'm just going to use log on my calculator. You would still be wrong, because to define more complicated functions as you move on in your mathematical career, you will want things more complicated than the logarithm, like say the die logarithm. The die logarithm is defined actually for a complex argument, but here just assume z is a real number. Z is the lower limit. You integrate z up to 0, it's often negative argument, in terms of log and dividing by t. So if you would like to build new functions to use in your life, which is very useful in many physics contexts, like the ADS-CFT correspondence in string theory, you want to build new functions with certain properties, and you need to know how to do that using the integral with its proper definition as a limit of partitions and not finding an antiderivative of some shit. Okay, I think I became more aggressive during that than I intended to, but I will do one more slide on misconceptions and then ask for your thoughts. So I'd like to just summarize some of the things that people think that are wrong in a calculus course and the correct version. So I've hammered and tried to beat a dead horse and tell you these many times, but these are just my pet peeves that I think one should be aware of. First, confusion. People think the word function means an algebraic formula, like something like x cubed, and then they think something like stars over Babylon is not a function, right? Because I can't write a nice formula for it, it's complicated, whatever. That is incorrect. The definition of a function is any collection of ordered pairs satisfying the vertical line test. Don't have to write a formula for it, just has to obey this definition. Second wrong thing, people studying limits who don't understand epsilon deltas think that the symbol limit as x goes to a of f of x is really just, a complicated way of talking about f of a, except maybe there's a point missing or something, so you just fill in the point. So they think this basically means f of a, but you fill in any points that are missing. Bullshit. You now know that you cannot speak intelligibly about anything in calculus if you believe this. You must know that the limit as x goes to a of f of x is the unique real number L with the property that for every epsilon greater than 0, one can find a delta greater than 0 with the property that whenever 0 is less than the absolute value of x minus a is less than delta, it follows that absolute value of f of x minus L is less than epsilon. The third one I won't belabor because we just saw it. This is the misconception that the integral sign means find an antiderivative and compute the difference. It does not mean that. You can use that to answer the question in some cases, but this is not that question. This is the question of what is the infimum of the upper sums, what is the supremum of the lower sums. The tool which answers the question is not the same as the question. Finally, we haven't seen this yet, but in the final unit when we do infinite series, people often come away thinking, oh, analytic functions are very nice. So it must be that most, in some sense, most functions that exist out there are analytic. And as you know, every analytic function is differentiable, it's continuous and integrable. So if we prefer, you could think of this as the confusion that many people think, most interesting functions are differentiable, or whatever. Finally, also false. I mean, if you're a string theorist and you want to do quantum mechanics using the path integral formulation, for instance, you need to find some way of integrating over all possible paths between 2 points. So now this is like an integral, except instead of a width, ti plus 1, instead of a width, I need sort of a distance between functions in function space. So this is kind of like, path I to path I plus 1, and I have to integrate over all possible functions that go between these 2 endpoints. So what does it mean to define a length or a measure in the space of functions? Well, it's very complicated, but once you define what it means to have a sort of volume in the space of functions, you could ask how big is a particular set of functions? Does it have a large volume? Does it have a small volume? As it turns out, the set of all analytic functions, the nice, smooth, differentiable functions, if you think of it, which is a very poor analogy, but if you think of it as a 3D space instead of an infinite dimensional space, roughly speaking, the set of analytic functions, the nice one, is roughly like a line in 3-dimensional space. Right? So it goes on forever in both directions, but it has zero volume. Again, as you were telling Berna, a line has no thickness, so it has no area and has no volume. So we say the set of functions is measure zero. Or in other words, it's not the case that most functions are analytic, in the same sense that it's not true that most points in 3D space lie on this line. In fact, almost none of them do. So we will see that more in the last piece. But okay, now I'm just making myself more angry, so I will pause and ask you, do you have thoughts or feedback on the confusions and the dead horse beating I've done?
I have no thoughts.
Okay, good. Are you convinced at least that the statements that I've written as wrong are wrong, and you are happy with the right ones?
Yes.
Okay. All right, last proof. Then I will leave you to do whatever catch work up you like, catch up on work. So I'll prove the second fundamental theorem. And you'll say this looks very similar to what we did a moment ago, because there was a challenge back here where we found some answer that, the integral from a to b of f is apparently g of b minus g of a. But this whole thing assumed something very strong, because we used the first FTC, which assumed that lowercase f is continuous. So I will prove the second fundamental theorem, which does not make this assumption. The second fundamental theorem, after going through the confusions, you don't have to assume f is continuous. You only have to assume f is integrable, and you have to assume f is the derivative of some function. Notice this does not imply f is continuous, right? You can very easily be the derivative of some function and not be continuous. Here's a very simple example. Take this function, f, and then take its derivative, which has slope 1, and then it has slope 0. Kinks turn into discontinuities. So it's very easy for you to be integrable and be somebody's derivative, but not be continuous. Right? So I'm going to prove the theorem in full generality. You're not going to assume continuity. But anyway, under those assumptions, only assume integrable and that you're some guy's derivative. Then, if that's true, then the integral from a to b of your function is going to be that antiderivative evaluated at b minus same thing evaluated at a. So this, I think, is the most beautiful proof in all of single variable calculus, because it ties together a lot of the powerful results. We're going to use the mean value theorem. We're going to cut things up into partitions. We're going to use the tools of infinite soup that we developed way back in chapter 1. And it's actually reasonably short. It's not even as long as some of the other proofs we did this meeting. So what's the proof? Okay, fine. Let P be any partition. We start with any partition of this interval, and I'm going to try to show that it satisfies certain properties regardless of what the points are. What do I need to do? Well, all I'm going to do is think about each of these t sub i's in the partition. I guess I should call these t sub I and t sub I minus 1. And apply the mean value theorem to the function g on this interval, right? What does the mean value theorem tell us? Well, we saw a long time ago, the mean value theorem tells us that there's always a point on the interval where the tangent line slope equals the secant line slope. So I've kind of skipped a step. You could imagine moving the ti's to the denominator on the left side, and then the left side would be the secant line slope between t sub I minus 1 and t sub I. And all I'm saying is that by the mean value theorem, there exists some point in here, maybe it's this point here, where the tangent line slope equals the secant line slope. It's one of the very powerful theorems of calculus. But anyway, so say that. So we can do that to every single interval. So in all of the subintervals, you find this point, call it x sub I, where g prime, again I'm applying this to g, which I can do. Yo, you should have asked me, you should have yelled at me. How do I know I can apply the mean value theorem to g? Mean value theorem requires continuous. I thought you said we're not assuming continuous. Aha, we're not assuming continuous for f. G is continuous. And we know this is true because g is an integral of f. Integrating increases niceness. Okay, so we can apply the mean value theorem to g. And I've done that. This step is very easy. All I've done is said, okay, well, g prime is f, so replace the place where the tangent line slope appears in the mean value theorem with f, using the definition. Okay, why is that interesting? Well, we're going to play some games with the soups and infs, so now we're integrating f, so just define these guys as usual, the m sub i's lowercase and m sub i's capital as the infs and soups on every interval. Now, all of these guys are going to be bounded, not that, by what we just saw, because if capital M sub I is the infimum, so this is less than or equal to every function output on the interval, then of course this thing times the width is less than f of x sub I, because this is a particular output, right? The lowercase m is a lower bound for all the outputs, the capital M is an upper bound for all of the outputs, so this particular output we get from the mean value theorem has to lie between them. Okay, that's fine. It's just the definition of upper and lower bound. But then we just take this f of x sub I and replace it using the mean value result. So I'm taking this right side, which is equal to this left side, and then plugging in, since that appears here, I'm going to plug in instead the g thing. The g of t sub I minus g of t sub I minus 1. So plug that in the middle, the other sides stay the same. Now I add them up. So we recall the definition of lower sum and the definition of upper sum is you add up either the inf or the sup times the widths. So just think of adding these guys up. 1 up to n. When you add them all up, of course, the middle piece is going to telescope. Why? Well, this is g of t1 minus g of t0 plus g of t2 minus g of t1, and as you've seen many times, these cancel pairwise, and you're left with just the last one and the first one, so they telescope. Okay, fine, so that means the lower sum is less than or equal to this difference is less than or equal to the upper sum. Right, so I've written that here in terms of lowers and uppers. But here's the kicker. And this is why I made a big deal about this a moment ago. At the beginning, we didn't pick a particular partition. We said let this be any partition, and then we just proved it. So if we said let this be any partition and just proved it, then obviously this statement that we've just found must hold regardless of what the partition is. So if this holds for every partition, then if you take the sup of both sides, or if you prefer, if you take the inf of either side, if this inequality holds for all of them, it must certainly hold for the least upper bound with the greatest lower bound. But by definition, those two bounds are equal, because this function is integrable, and if they're equal, the only thing that they could be equal to is this guy who lies between them. So that's the answer. That expression in between g of e minus g of a is the value of the integral. And all we needed was 2 slides, right? Just mean value theorem, get these derivatives, replace the derivatives by the original function, telescope these guys, and then that gives you the answer. So that's the second fundamental theorem. Okay, I have one challenge, but thoughts on this proof?
I do not have any thoughts. This is all sufficiently clear.
Okay, good. I think it's very important to understand this proof. Alright, good. Let's do one example then. So, suppose f of x equals 1 over x, and pick some point 0 less than n is less than a. So they're all positive. And now I ask, we want to integrate 1 over x dx from a up to n using that fundamental theorem thing, so you don't have to do any upper or lower sums. What are the steps? Well, I guess I should find an antiderivative. I should find a function with the property that its derivative is 1 over x, and then I should take the difference of that antiderivative at the top and bottom. So what should I do to evaluate this thing?
Well, I believe we can start by saying that this is equal to negative the integral of 1 over x on a to n.
Oh, yes, I think I did this backwards. Okay, yes.
Disordered.
Yeah, sorry, I had a typo. That's good. Okay, we'll just proceed with the problem as written. All right.
Okay, and I believe that the natural log, well, natural log's derivative is 1 over x.
Good. So if this is f, then g you say is log x, and then g prime is 1 over x. Okay, sounds good.
So this is simply g of v, well, quote unquote g of v minus g of a. So we're going to have g of a minus g of n.
G of a minus g of n. Okay, good. So can you plug those in and simplify with our log of a sum or difference rules?
So this is going to be log a minus log n, which is equal to log a over n.
Looks good.
Whoa.
Sorry, I was just being a troll. Good, yes, indeed. So, I think I screwed up the signs because I should have had it going the other direction so it wasn't an overall minus sign, but yes, I wanted it to be integral from n up to a of 1 over x, which is log a minus log n, which is log a over n, or if you prefer to write it with a slash, write it like this. Good. Indeed, our first integral calculation which did not require lower and upper sums. Good, 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 good. All right. Parting thoughts or comments on this guy?
Oh wait, it's Logan.
You didn't see that till now.
No.
Okay.
That took far too.
I thought you